All right, here we go. So this is probably about 10-slide series of questions. I mean, we're not done after that, but like this scenario is super important. Like you're applying. I'm not teaching anything new. This is just that you are applying this. Okay, go. Thumbs up when you have an answer. Thumbs up when you have an answer.
You almost got me. I think he did give me the answer.
Correct answer is
B.
Oh, I about got myself. You are correct.
Yeah. I didn't realize the +3 on the outside, so I was about to say. Wait, which one was the answer?
It is B.
Awesome.
Like I was like, that's 4.
Yeah, that's what I did first, but 3 + 1 is
Okay.
2.
Is everybody good with that?
No, it's not.
Total uncharged. Total charge enclosed +2. Okay, with the Gaussian surface. Okay. Okay, this is asking for electric potential. Thumbs up when you have an answer.
Oh, wait. That's easy.
And leave.
There are multiple ways you can remember to get this into the and I don't know any of them.
Correct answer is
B.
B again. Okay. You consider this as a point charge infinitely far away of a total charge of +2. If you integrated this from infinity to this, you would get this. Okay. Good with that? Okay. Electric potential at this location. Electric potential at that location. Inside the metal. Bless you.
The answer that I want is not on the board.
So it's probably not right.
Thumbs up when you have a guess. This could be a good conversation. Yeah, have a conversation.
Wait, hang on. Sorry, I put K over R. He said it's on the outside of the ring. It's K over R using our language. And because there's no electricity inside the node, it means that there's going to be like slope to 0. Miley, can I have a Christmas light? I'm doing it for sure.
Yeah. Okay. What do you say? Correct answer is A. Good job. I heard a lot of good stuff. You know, the electric field in the conductor is equal to 0. Therefore, there is no change in the electric potential. Okay? The electric potential, this is the outer radius, R3, and therefore it doesn't change.
Would it be the same as the inner radius too? Because
Crazy.
I don't know what the answer is.
What do you say? Correct answer is A. Does not change at all.
Why not? Why not R2?
Because what we're doing is when we're finding the electric potential, we're integrating from infinity.
Okay, and at that
So
from infinity, and then it doesn't change.
from infinity, we have this value, and then from this value in, it does not change at all. Okay, good with that? Has the same electric potential. All right. All right. At that point, so this is an electric field.
Oh boy.
Thumbs up when you have a guess.
Ooh. Interesting. Wow. Yes. I don't know how.
Thumbs up when you have a guess.
Do it, Bradley.
Have a conversation.
It's wrong because the outside one is true.
I remember something like that.
Yeah.
Also, if you also fit in that, so
I don't know.
Yeah.
So I drew a circle inside the metal circle on the outside, a Gaussian surface, and said,
but then when
"Hey
it's outside,
man,
it's
it's in a conductor, man.
You don't
so the net electricity is zero. But
That's what I'm
you
saying,
know, it's in a conductor shell, man. And so I have no idea what I'm doing.
D for Gaussian surface.
D for that seems right, probably maybe.
Yeah.
Correct answer is D.
Yes.
Okay, dangerous dinosaurs. You are drawing your Gaussian surface here. The enclosed charge is just negative Q. You are this distance away from this point charge. You consider that as a point charge. This, the net electric field from this outer ring, even from the inner ring and outer ring, is 0.
Is that just hollow planet?
Hollow planet, yep.
I want iron today.
Oh, this
Okay.
is field, not voltage. Wow.
Yes.
I can barely read, so.
All right. Whoa, whoa. You good?
No.
Okay. Well, get it now before, like, we're just going deeper.
Like a pool.
Yep. So Gauss.
The Gaussian surface thing on the inside. Where's the K Oh, that's the electric game we established.
The answer is D.
The
D.
answer's D. Oh,
Dan-
okay. I was
Dan-
like, what the heck?
Dan-
Okay, I thought
Dangerous
I
done.
didn't think this was roll E equals. I thought it was
Okay.
B equals. So
So
okay, I got it.
here we go. So same location.
Oh, funny.
Okay.
Tricky.
How? Oh, we're gonna find the electric potential. Easily distracted. Surprised you guys didn't discover that in elementary school.
My brother.
Because they probably never had raisins in elementary school.
You know you can do that with a piece of grass. Yeah.
Why would you put that in your mouth? That sounds like an easy way to die.
I'm doing that.
Thumbs up when you have a guess.
One of them feels relatively obvious, but I feel like that's also wrong, but that's what I want to say.
Probably.
No, I mean, like, there's only one option that's even possible.
Yeah, that's even possible.
If you're playing.
Okay, correct answer is
E.
E. Every egg.
Yeah, I was confused because there were 3 times the most weighted.
Okay. So we have to start from infinity of our way. We've got that expression until we hit this surface, and then it's 0. This is just me trying to teach you. I would, if I was in your shoes trying to calculate this, you can just omit this step.
You pull out the
It's
zero. And
0. Okay.
So this is the one case where you can't actually pull out the zero and it works.
Okay. And then here you start at 2, not at 3, but at 2. Probably should have put, that would have been better. Anyway, that would be a good distractor question. No. Here, here would be a good distractor. This is repeated here, and then going from R3 to R, and then repeated this. Forget that. So if I did 3, that'd be a good distractor.
Oh, yeah, it would. I would have
Okay.
fallen for it.
For my future career.
It's not because the other one is 0.
Okay.
One of them thing will be 0.
The last one.
This is electric potential. Tell your neighbor.
Because it's not going to see that the net charge on the outside. Positive 1 goes on the inside.
I'm saying A or B, but I don't know why.
I don't think R2 is.
Yeah,
I have more than that. It's higher.
Okay. So we're going back to this. We know this value. Oops, sorry. So that's Okay. So it's either A or B. Ah, wrong way. Ah. 0, don't have to worry about that one. This is going to be, this is just Q, negative Q. You have, neither of these are 0. So when you do final minus initial, you get that. That makes sense?
So the answer is
A.
I forgot about final minus.
So here we're starting at, this has 0 electric potential infinitely far away. So we only get one expression from this. Here, the electric potential is not 0 here, nor is it 0 here. So we get final minus initial.
okay.
Good with that?
Yes.
So that's why you have 2 there.
Okay.
Okay.
Understood.
Now we're in the middle there. In the tell your neighbor. Have a conversation.
I was doing what I was doing was on the outside of the ball, so we could like
So far, all the ones I missed because I can't read, and I
Oh.
Correct. Okay, so is everybody good with A? Okay, this is the same expression as this, just our value of R here is R1 because it doesn't change, electric potential doesn't change from this point on in. Okay, so try to mentally sketch the electric field.
oh boy. E is for electric potential.
Yep.
V is for volume of electric field.
That's so weird.
Yeah, that really is. Ooh, one of these is the
Where
derivative
does
of
R start? 0?
What?
Like the middle?
Huh?
Is that like R?
R, yeah, R, when R is 0, that's this point here.
Oh, that's weird. I was going backwards.
It's easier to work backwards, but that's just me. And perhaps you.
That's fun. Okay.
I'm going with A.
What?
She's going with that? It was my left hand.
Proud of you.
A. Apples.
There must be context I'm missing.
No.
Okay,
I'm making a bad joke.
so
Okay, that's the context I was missing. I was expecting the joke to be funny.
Should have put something to me.
we are, so we know that electric field inside the conductor is 0.
Yeah. Yeah.
Good with that?
Which then the slope on
Okay. Now, this is positive out here. Electric field's going outward. Okay. So this in here behaves like a point charge. Well, whatever. Okay, you know there's a horizontal asymptote. Okay, and then that drops to 0 there. This positive also, it's 1 over r. This is 1 over r squared. Okay. Here, this stays the same. Good with that? Okay. And then from here to here,
Something seems off.
is a negative charge. It might not go as high.
It should go. It should
This-
be,
this-
it should be less than the other.
Yeah, this we're gonna make. I'm gonna make this higher, just because it's 2q.
Potential when it's like bigger than R3, shouldn't it be like a line?
Say it again.
Oh wait, never mind. Just kidding.
Are we good? Okay. So this I'm gonna make lower. Good with that.
Nice.
And then electric potential here. Did we go 0? Hold on, I'm thinking. So as we progress, we're going lower in electric potential.
You know what I mean?
Oh, bother. Okay. I think. Should have gone up higher on this one. That's going to help me. And then because this is less charged than this, it's going to decrease, but it's not going to go below 0. Okay? And then it's that's a rough. Like there's a point at which it just goes flat. Okay? There's that.
Yeah, that looks
Might be
looks good enough.
after R3.
Yeah.
If they're the negative derivative of each other, right? Then that's right. Never mind.
We're good?
I'm good.
Okay. So this has a negative slope. Okay. And it's increasing as we go that way, meaning we have a positive value that's higher here, lower here. Zero, zero. Here we have a positive slope. So we have a neg. Ooh, yeah.
I knew something was wrong. I didn't know what it was.
One of them is.
So how about you?
Like this.
Yeah. Okay.
Oh, yeah.
Okay, that
Yeah, like that. Yeah. Good with that.
Yeah, because that was there you go. Because you end up subtracting one.
That's good for your response problem.
Yeah, because you end up subtracting that one. You end up subtracting that one.
How do you what? This so electric field is equal to negative derivative of electric potential.
No, yeah.
Oh, sorry.
Like,
What's your question again?
like, how do you know, like, if you don't have values, like, which, like,
How high it
yeah,
goes?
like how high? Not
So-
like individually.
So here outside the total charge was positive 2. Inside here the total charge is negative 1. So I know out here has to be higher. Like the field is going to be stronger here than it is inside this region here because of that charge. And therefore this is not going to go below 0 because this value is going to be greater than that value, that negative value. We're going to decrease, but we didn't. If this was like a -6, then it would like drop below here. If this was a -6 charge in here, this would go below that line. Or if this was -3, then it would end up back to 0 here. Okay, good with that? All right, so, I know. This is just me like giving you a foretaste. You don't have to do this. Okay? So, let's say if the electric field is changing in 3 dimensions, we can find electric field from the electric potential as the following. So this is known as a partial derivative. Okay? I'll tell you here in a second. So we're finding the derivative of each component in x, y, and z independently. Okay, and so what this does is we find that here's how you do this. Okay, so let's say we take the partial derivative of this function here in terms of x, y, and z. Okay, so
Y and Z become constants.
So here we're going to find the derivative of this function with regards to x, and x and y and z become essentially constants, okay, coefficients. So take it, so this becomes 2x to the first, y. Hey, it sure is right here. You're welcome. Me too, Sophia. Okay, and here's x to the first. Okay, that's just a coefficient. Okay. If we take it and then we look at it in terms of take it the derivative in terms of y, it's y to the first. That just becomes, this is the coefficient. There's no y expression here, so that drops to 0. And then over here, we take it with regards to z. There's no z here, so that drops to 0. This is z to the third, so we bring that 3 down here, square that. X is just a coefficient.
They get way more annoying than that.
I know. Okay, so, but that's the general idea. Okay.
If you ever need to do this in your 89, by the way, you know how you have to do d and then insert the function comma x. That means with respect to x. So if you'd rather do it with respect to y or with respect to z, you can use y or z instead.
Nice. Okay. So this is the gradient, which means you're taking the partial derivative, okay, of x, y, and z. This is called del. Okay. It's a gradient. Okay. So
Unrelated to gradients.
correct. So this can be written like this, or it can be written like this.
Why would you write vectors like that?
Vector notation.
Use ket notation.
Okay. Good with that. All right. So the positive gradient looks at the slope at the field. So this would be graphing the gradient. As it gets steeper, it's a greater value. Okay, bigger arrow. Okay. As it gets shallower, it's a less, and it's pointing uphill. Okay. So does that make sense? As you
that's slope.
slope.
Yeah, I can't picture things, so that's.
Three-dimensional goal.
Okay.
I can't picture two-dimensional things, so I'm
We're
completely
doing a
lost.
three-dimensional thing in a two-dimensional space.
Yep. Okay. So the negative gradient is the same idea. It just points downhill. Okay. So here it's steep. Therefore, you have a higher magnitude of the gradient, but it's pointing downhill.
Negative points downhill.
Yep. Positive points uphill. So guess what also points downhill? Electric fields. So when we find the electric field is the negative gradient of electric potential. You don't have to know this. This is not. I mean, you can write it down if you want to. This will help you in college. This is not going to help you. This is not going to help you for the AP exam. Okay. So it points in the direction of its most rapidly changing position. Okay.
How is that different from an antiderivative?
Really different.
Oh.
It's closer to a derivative.
Oh, is that what I meant?
Yes. So with derivative, you're just along one axis, the x-axis, like you're with regards to the x. This is like x, y, and z. Yep. Okay.
They're nothing like an antiderivative.
Okay. So here we see a dipole in the mountaintop and sinkhole. This is the positive gradient, how it's pointing uphill. This is what we use for electric field, pointing downhill.
That's so great. That's just because Gilmore taught us this stuff last semester.
Oh yeah.
It's cool coming back to this and seeing like normals and stuff.
Yep. Good with that. So that's just a foretaste, Micah. Just the math. It's just it's easier to start with math. In math class, it's easier to start with a positive and then just switch it. We just happen to have a physical representation.
It's the same Franklin effect.
Say it again.
I was thinking at what point would it be helpful to have positive gradient, thinking about like field choice and
Not for electricity or not for statics. Okay. All right. Oh, we're not done. That was just.
Smiley, you did a great job teaching us.
Thanks. No, just kidding. That's just halftime. All right.
We're going way after the bell, guys. Oh no, not
All right. So capacitance. You're gonna need this for mastering. You're welcome. All right.
Thanks, actually. I'd rather know it. How should you mastering without it?
All right, so capacitance. Okay, this is the ratio of how much charge can be stored for a certain electric potential difference across two different points. Okay, you can, this scenario here actually can technically be considered, you can find the capacitance of a dipole if you really, really wanted to.
That's a weird.
I'm not suggesting that you're going to make that a capacitor, but you can find the capacitance.
Either my vision really bad, or those are very weird circles.
Those are weird circles.
Okay.
Great question. So the unit is coulombs per volt, which is a farad. Okay, farad. A lot of times it's measured in microfarads because your charge is going to be in microcoulombs.
Yeah.
Or nanocoulombs. Or,
yeah, what about 100 millifarad capacitor? I've seen one of those.
yeah. Okay.
No.
So here, just a quick review. This is the capacitance, can be measured either experimentally by measuring the charge on the plate, and that's a single plate. It's not combined of both. It's a single plate over the electric potential difference across the two plates, or you can find the capacitance by the geometry of the parallel plate capacitor, where you have epsilon naught. This is not something different, still epsilon naught. Bless you. The area over the distance. And I'm pretty sure that's on your.
Yeah, it is. Wow. I remember using these equations.
Yeah. Okay. So, yeah, capacitance by definition. Okay. So, get to that. So, what happens if you're given something that's not a parallel plate capacitor? Not kidding. Okay, so what we've got is two spherical shells. One's positively charged, one's negatively charged, and it's set up in a capacitor type fashion. So this is
are the surfaces of the spheres equidistant?
Yes.
Okay.
It's centered on they're centered. I don't know if this is a practical capacitor, but they can come up with some crazy things.
It wouldn't be useful for storing things because at least it won't be useful for circuits because you can't interact with the inner one.
That would be difficult. Okay, so what our strategy is this. In order to find the capacitance, we're given the charge plus Q minus Q. So we need to find the electric potential difference between the two shells. The electric potential difference from this point to this point. Okay, so we're going to need to find the electric field in this gap here.
And we don't care about stuff outside.
Correct, because if we did the Gaussian surface outside, then total enclosed charge would be what? Zero. So our electric field outside here would be 0. You good with that? So the only thing that we care about is in this gap, because inside here the electric field is 0 as well. No enclosed charge. So right here is what we're looking for. So our Gaussian surface we're going to put inside here. So we've got electric field is times 4 pi r, squared. So that's a surface over Gaussian. Okay. Total and charge is actually just plus Q. Total enclosed charge over epsilon naught. Okay. So we find that the electric field is just equal to 1 over 4 pi epsilon naught Q over r squared.
It's almost like it's a plate charge.
Mm-hmm.
Almost.
Good with that?
Yeah, 1 second.
So this arrangement, it is more complicated than a parallel plate, but it's not hard to calculate. So this is why it's a great response question, or even a multiple choice question. It like freaks people out, like, ugh. But if you like evaluate it, you're like, oh, that's not so bad. Okay? So then our next step is to employ. So this was Gauss's law. Oh yeah.
Yeah, we take 2 exams. You signed up. You had to sign up for 2 exams.
Darn.
Wait, did you not sign up for both?
Yeah. No, I'm kidding.
That's a bummer. Okay. So. All right. So we've got that. Okay. What is our? Don't say it out loud. I just want you to figure it out. What is our limits of integration? Have a conversation.
I think the gas is. Oh, but it would be the same as that. Why not? What would this? Oh,
Right?
Would we set up 2 of them? It's different.
I think we're gonna get there. Yeah.
Okay. Correct answer is.
RB to RA.
Yep. Final minus initial. Okay. Why? Great question. So we want to start where the electric potential is 0. So infinitely far away, the electric field outside this Gaussian or outside of this is 0. So there's no change in electric potential. So electric potential is 0 here, and because it's a conductor, here as well.
Wait, why is electric potential 0 there? Because
So the electric potential is 0, infinitely far away. There is no electric field out here. Because if you do a Gaussian surface outside here, the total enclosed charge is 0. So there is no electric field, so there's no change in electric potential, so the electric potential remains 0. Here, it's a conductor, and so it doesn't change. So the point at which, so this is a great 0 point. And we're going all the way to this outer red rim of the capacitor.
We only care about the voltage across.
Okay. So our electric potential difference therefore becomes final minus initial. So we've got 1 4 pi epsilon naught q over oh, stop doing shortcuts. At this negative final minus initial, and then applying this negative, you just get, bless you, you get 1 over RB minus 1 over RA.
You should.
Do what? Yes, 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 you would. So that's a negative. That's a negative. Good call. So we're back to RA minus RB. Good catch. Thank you. That negative cancels with this negative. Good with that. So that is our expression for electric potential difference. And then
And since we're going for voltage across two things, we can just assume we can actually just still just do final in it. We still have to go to where the voltage is zero because we only care about the change in voltage, not the absolute voltage.
so our capacitance is equal to charge over voltage, which is plus Q over all this.
And for I epsilon naught goes
There you are. Okay. Good.
How do you pick the charge? Like, how do you decide what the charge is on the capacitor?
Great question. It's one of the plates. Mm-hmm.
Say that again?
So a charge on one of the plates, and a capacitor, they're going to have the same charge.
They have to. Never mind.
Don't have to. What would you do if they weren't?
but which way? If that.
You choose one, and then it says incorrect 5 remaining, then you choose one.
Yeah, true.
That doesn't work on the AP exam.
Oh, well. Just
Hmm.
finish one.
Request.
Okay, for
Alright.
any real capacitor that's hooked up to a circuit, that the charges would equalize anyways.
Right. Man. Yeah, I don't think you're going to expose to one of those, but I'll look that up. All right. So for so for this, we're going to do the exact same procedure, same thought process. We've already
We
have already figured out the expression for the electric field. With I'm going to erase all this. Are we okay with that?
Yeah, I can't really see.
Okay. So if you have this coaxial cable, okay, we're going to find the strength electric field. So they give you this here. This is what the problem is. You're going to do a Gaussian surface for this inner part here. Okay, which is what we did here. Okay, so the amount of, and we've done this a couple different times. Okay, I found the strength electric field uses Gauss's law. You have a linear charge density, and then we integrate that, and we get this expression, which we make this point here 0. Okay, this distance away, so we get their expression for this, and then all of a sudden, our capacitance is just charge over voltage. Our charge is equal to lambda times L over that expression. Or B.
That would be alright.
because we're starting here and we're going this way. Here's RB.
Oh, okay. That's the outside. That's okay.
RB. Okay. R equals RB. I think that might be RB minus RA. That seems to be right. That gap. You're right. It's not right.
Why? I don't know why we're making it 0 to RB.
Big R is R. Capital R is RA. So RB. I'm good with that. Okay. But that's the general strategy. Okay. So if you're able to do most of all the mashing, if you see anything about dielectrics, that's tomorrow. Yeah.
Always set B equal to 0 at the outer radius?
Yeah.
Yeah, and then we just don't have to worry about all the other going to infinity stuff.
For this one, you don't do the infinity.
Yeah, well, we don't ever have to do the infinity, right? Because it's just the difference across the two plates is all that matters.
Because
Right.
charges.
So you never have to worry about it.